Hello, David Lonsrich here. I want to keep changing that intro, but I just have no imagination. Anyways, this is the third of three videos for this week, and thankfully there is only one more week of this. I don't know how if I can do any more of these videos. I've already got a stockpile for next semester. Hopefully, I don't have to use them. Anyway, so this is a video that's about a topic that is not usually included in a endocrine system presentation, but it is an important topic to learn about. So I begin with this: like, how much hormone do you need? Well, as it turns out, the molar concentration, molarity of hormones is usually very low to generate a systemic effect. So 10 to the minus 12 molar concentrations, or moles per liter, molarity. That's really low. Now, exactly how low is that? Well, I did some math. I'm not sure if I did it correctly. I did it several years ago. I haven't double checked it recently. Um, but let's do this. Let's assume a certain amount of water and a certain number of moles. I put 10 to the 11. So obviously, I don't even know. Obviously, let's just say it's 10 to the 12 molecules. You might wonder, how do I get that Avogadro's number, right? So 10 to the 12 molecules, which seems like a lot. That's like a trillion molecules. Just how much is a trillion molecules? It's this much. Take 1 grain of sugar from this container, cut that sugar granule into 1,000 pieces, then take one of those 1,000 pieces and cut it into another 1,000 pieces, and that'll give you about 10 to the 12 molecules. Now, why is that important? Because what it's trying to demonstrate is that small changes in chemical composition within the body can have very profound effects, as illustrated by hormones. But that's not the only kind of chemical that the body is exposed to. And those chemicals that I want to focus attention on today are endocrine disruptor chemicals. Those that are generated from the outside and that can have effects on the endocrine system. Then you'll see some examples of those. This is just an illustration of what those effects can be. Impacts at very low concentrations, often below the no effects level. Again, that goes back to this point here that it doesn't take a lot to have a big effect. Among their effects on endocrine system function, they can mimic endocrine hormones, they can block endocrine system pathways, or they can inhibit normal cell function. Those are just some illustrations. I have a link for a paper for you that you should read, a very short one, on Canvas. Here are some examples of endocrine disruptors. Some of these you have heard of before, but maybe not in the context of endocrine disruption. Bisphenol A, which is chemical that is found in, or was once found, maybe still is found in plastic. Pesticides like DDT, you've probably heard of DDT before. You've heard of drugs like DES, which actually used to be administered to pregnant, I think it was to pregnant women, or maybe to induce pregnancy. Anyways, it generated a developmental effect on embryos that produced, I'm not sure, it wasn't good. It could have been deformities or mental developmental issues. Then there are phytoestrogens, which are plant estrogen mimics, soy-derived products. What the heck do these things do? So I'm not going to talk about all of them. I'm going to talk about just two that I know really well. One is DDT, and the other is atrazine. DDT is a chemical that was developed after, or just right in the middle of World War II. And one of its objectives was to help rid the world of malaria and to protect crops. DDT was known as a very effective insecticide. And so it was applied very liberally. Here is an example of what was happening in the early days. They'd have trucks driving down roads that would fog people. And it was believed to be innocuous and very safe. And it falls into a class of compounds called organochlorines, which, as it turns out, are really bad for animals, not just insects. And DDT acts as an estrogen mimic, estrogen mimic disrupts the endocrine system of birds by interfering with calcium metabolism, and it produced weak egg shells and feminized frogs also. But this is the one that was the most significant part of the story. Some of you probably know that the bald eagles back in the 60s almost went extinct in the lower 48 states. Back in 1967, there were probably 20 or 30 pairs of bald eagles in the state, and now, in this number in 2018 is about 1,700 pairs. Bald eagles are really common, but they were not back in the 60s. And there were other birds like peregrine falcons and cormorants and pelicans and all sorts of other predatory birds that were affected by the endocrine disruptor effects of this chemical. Here's the pathway of how it happened. Eventually, we got rid of it because of the effects it was having on wildlife. We don't use it legally, at least not in the United States, but it is still used in other parts of the world. And one of the reasons why is because it's still very effective at killing mosquitoes that carry malaria protozoan. Okay, next one. Actually, still staying with DDT, and I'm not going to talk about this one, but this is actually kind of interesting if you're interested in ecotoxicology. It's about like how does a chemical become problematic to the animals if it's not really detectable or causing problems in lower parts of the food chain. And the way it works is that some of these chemicals can biomagnify, and they biomagnify because they accumulate in the fat, and DDT, which degrades into DDE, has a very long half-life and accumulates in the fat tissue. And so once a shrimp is eating something that has very low concentrations of DDE, they accumulate more of it. The next predator eats some of this, they get more of it. So it magnifies into the higher level predators, and this is why predatory birds were hurt by the DDT threat, not other animals like fish or sparrows. It's the high-level predators, peregrines, bald eagles, etc. Okay, moving on. What I want to finish off with is atrazine. So atrazine is a chemical that is now still widely used in the United States, applied to crops, corn principally. It is a herbicide that targets weeds, but it also has a side effect, although the EPA will not agree. And that's one of the reasons why it's still on the market. But the evidence is pretty compelling. And I know this because I've spent a lot of time reading up on this topic. Is one of the most commonly used. It turns out the most commonly used one is probably Roundup or glyphosate. Contaminant of ground and surface water, and it mimics the function of aromatase, which catalyzes conversion of testosterone to estradiol, and those would be female hormones, which trigger the maturation of oocytes in females. So what happens is atrazine is mimicking the function of this thing. Here's testosterone. So if a male normally doesn't produce a lot of aromatase, but if the male's been exposed to atrazine, it's going to have a lot of testosterone converted into estradiol. And that results in the feminization of the males, and hence we have feminized frogs. and other reproductive effects. The evidence is pretty compelling. Frogs that should not have eggs in their testes in areas in both natural settings and also experimental settings. Frogs become feminized when exposed to atrazine. So this is an endocrine mimic. Now, of course, you might say, well, who cares about frogs? The argument has been made that this is not just limited to frogs, it also may affect human development as well. And this is still an open question, and I'll leave it at that. Those are examples of molecules that are produced in the environment that have effects on the endocrine system, and we call them endocrine disruptors. Okay, thanks. Bye.